Hello everybody, welcome to today's video. Today we're going to be picking it up essentially from where we left off last time, talking about the fundamental identities, and we're going to start moving into some more just different trig identities that we can use to simplify and solve problems. So today we're going to be looking at the sum and difference identities. So we'll see what they are. We're going to derive the difference formula for cosine and then talk about how we could get the other ones from that. We'll derive the sum formula for tangent and then maybe talk about how we could get the other version of that one, and then we'll use all the different formulas to solve some problems here. So, all right, the motivating idea here for what we will develop is it true that sine of alpha plus beta is the same as sine of alpha plus the sine of beta? I think it's a natural question to ask. If you have a sum of angles, can you just split that apart and look at the sine of each angle individually and add them together? So let's just take a look here and see if this is true. I'm not saying it is or it isn't, but let's take a look here. So what this is saying is, if I just pick some numbers, does sine of 30 degrees plus 30 degrees equal the sine of 30 degrees plus the sine of 30 degrees? So now we are just asking the same question, but we're plugging in just some tangible numbers here that we can compute the sine of. So now the left-hand side says the sine of 60 degrees. Is this equal to the sine of 30 degrees plus the sine of 30 degrees? Well, we know that the sine of 60 degrees is the square root of 3 over 2. And we're asking, is this equal? And we know that the sine of 30 degrees is 1/2, and the sine of 30 degrees is 1/2. So what we're getting here is the square root of 3 over 2 equal to 1? And of course it isn't. So we are not getting a true statement here. So it is not true in general that the sine of alpha plus beta is equal to the sine of alpha plus the sine of beta. But what can we do if we do have some sort of addition or subtraction of angles here? Is there some sort of relationship that we can use? And the answer is yes. And so we'll go through and we'll try to develop some of those here. So here are the sum and difference formulas for cosine. So we have cosine of alpha plus beta is equal to some combinations of cosines and sines of alphas and betas. So getting this memorized is kind of tricky, but maybe we'll talk about some of the ways that I keep them straight in my head. But here we have cosine alpha times cosine beta minus, so here I am noticing that the sine originally here is positive, and now it is minus, something to keep in mind as we're trying to memorize these. Sine of alpha, sine of beta. So at least here I'm noticing that the cosines are together, and we're looking at each individual angle, and then we're subtracting. So this is different than the sine we started with. We're subtracting sine of alpha, sine of beta, and those are grouped together here. And then we see kind of the reverse here for cosine of alpha minus beta. We're getting cosine alpha, cosine beta. Plus, now we had a minus in our argument here, and now we're getting plus sine alpha, sine beta. So just some things to point out there about the looks of these formulas. But let's prove it, or at least we're going to prove the difference formula here. So the way that we're going to do this is kind of this weird argument. We're going to get some different chords on the unit circle and compare those distances and see that we just happen to get what we claim we are getting here. So we're focusing on this guy here, the cosine of alpha minus beta, and we will show that this is the cosine alpha, cosine beta plus sine alpha, sine beta. So what I'm going to do first here is I'm going to consider this point. Let me write that a little better. Consider this point P, and it is going to be at cosine alpha, sine alpha, meaning that wherever this lives, and we're going to put it on our unit circle, must have an angle of alpha. So I'm just going to throw it over here in the third quadrant. I'm not saying that it has to be in the third quadrant, it's just where I'm putting it for the sake of this diagram. So here is P, and it is at the point cosine alpha, sine alpha. And so we know that this angle here is alpha. Okay, so this is an arbitrary argument. I'm just placing it somewhere here so that we can start talking about what's what. Next, we're going to look at another point on here. We're going to just consider some other point. We'll call it Q, and it will be at cosine beta, sine beta, which means that its terminal side is somewhere on this unit circle with an angle of beta. So we're just going to squeeze this in over here somewhere, and we will just call this point here Q. And this is going to be the cosine of beta, sine of beta. And that means that this angle here is beta. Okay, so, oops, need another parenthesis there. So now I want to note something. I want to note that the angle, if I label this, the origin O here, that the angle POQ is equal to alpha minus beta. So if we just take a look at that angle there, this angle here must be alpha, since the entire yellow distance is alpha, and then we need to subtract off that little beta portion there, this beta portion here, to just get the kind of in-between arc length that we're looking between, that arc length between P and Q, or that angle POQ. Okay, so we've got that as just a note here. So what I'm going to do now, I'm going to erase what I wrote here on the circle, but what I'm going to do now is label, whoops, switch back to my pen. We're going to label this point A, point A, and actually let me move it down. I don't need to write point. We will label this point A at the cosine of alpha minus beta, sine of alpha, minus beta. So we're just looking at this angle we created with POQ, and we're going to just try and get that angle on here by itself. So A is going to be kind of over here if I'm thinking about the difference between P and A being the same as the distance from the x-axis to Q here, since those will be the same. So here is the point A, and it is at cosine of alpha minus beta, sine alpha minus beta. Let me get those all in parentheses there. Okay. So we are getting this angle here is alpha minus beta. Okay, so we've got some different angles on here. Oh, and there's actually one more point that I want to label here, and that is point B, and this is going to be at 1, 0. So we're just going to put another point right here at 1, 0. It's already kind of labeled on here. So now what we are going to show is that this length here, so we'll do this in blue, from P to Q, so we're getting this line segment from P to Q is equal in distance to this line segment from, not A to Q, but from A to B, is equal to this line segment from A to B. And we can get that that's true because if we want to show this explicitly, we know that the triangle created by POQ is congruent to the triangle created by AOB. So what we've got so far is just that these chord lengths from PQ to AB are equal to each other. Their distances are equal. So what we're going to do now is directly compute their distances, set them equal to each other, and show that we get the difference formula for cosine. So it's kind of this convoluted argument, but it's going to do exactly what we want here. All right, taking a look at this next slide here, I've just got a summary of everything that we saw on the previous slide, just kind of getting things grouped together and in one place. But what we saw is that this distance from PQ here, this chord PQ, is equal to this chord, this distance from A to B. So these chords have an equal length. So what we're going to do is just compute these distances directly. So if I want to find the distance of this chord length PQ, or this line segment PQ, I'm going to use the distance formula. And the distance formula is, just to maybe remind you, the square root of the difference in the x values, so x2 minus x1 squared, plus the difference in the y values, y2 minus y1 squared, and then take the square root. So this is just actually an application of the Pythagorean theorem, if you ever can't remember what the distance formula is. But now we're just going to plug things in. So my x values here are going to be cosine alpha and cosine beta, and my y values are going to be sine alpha and sine beta. So we're just going to get those plugged in here. I'm going to use the bottom of the screen and then make things smaller and move them up just to give myself some more space to write here. But what we're getting is the square root of my x values. So let me say these again as I'm writing them down, or highlight them rather. My x2, we can call that cosine alpha. It doesn't really matter the order here, but we're going to get cosine alpha minus cosine beta. That's the difference of my x values, and we're going to square that, and then we're going to add to it the sine of alpha, my y value, minus the sine of beta, all being squared here. So let me make this smaller, and we'll move this up, but that's our first step. And now we just need to start multiplying things out here. So in our next step, we are going to get the square root. So cosine alpha minus cosine beta squared is going to give us cosine squared alpha minus 2 cosine alpha cosine beta plus cosine squared beta. So that's just squaring out this first half here. And if I square out the second half here, I'm going to get plus sine squared alpha minus 2 sine alpha sine beta, and then plus sine squared beta. Okay, so there we've got that just all multiplied out. And now what I'm seeing is there are some groupings of Pythagorean identities in here. So let me just make this a little bit smaller. Oops. And we'll move it over here. But what I'm noticing is that now we have the square root, and I'll color code some things here, a cosine squared alpha and a plus sine squared alpha. So those are just one Pythagorean identity. And then I'm also noticing I've got a cosine squared beta plus a sine squared beta. If I group those together, we just get 1. So I've got 1 plus 1 there, and then the rest of this says minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta. So maybe just one more step here to simplify. Now this is a lot of writing, but we're going to get 2 minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta. Okay, so that is the distance of this line segment PQ. So kind of ugly looking, but it is what it is. And you might notice that if we're trying to show that we're going to get cosine alpha cosine beta in here, where I can see a cosine alpha cosine beta showing up here, and we should be getting a sine alpha sine beta showing up, and I can see a sine alpha sine beta showing up here. So even though this is a goofy looking expression, it does have the parts that we need here. So I'm feeling good about it so far. Next, we're going to look for the distance of the other chord from A to B here. So moving to our next slide, I'm just adding this new bit of information that we just found, that the distance from P to Q is the square root of 2 minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta. All this is kind of a mouthful here. So we're going to do the same thing that we did to find this distance from A to B now. And we are going to do the same thing that we did before. So let me write it down here. The distance for this line segment from A to B is going to be the square root. This time my x value is going to be cosine alpha minus beta. So cosine alpha minus beta. And I want to subtract from that just 1. So this one starts off seeming like it's going to be much worse, but it actually turns out to be not too bad. And then we want to square that. And then to that we want to add the difference of the y values. So the y value here is sine alpha minus beta. And then minus 0, which we don't really need to write the minus 0 there, but we will just for completion to show it. So let me make this a little bit smaller and move it up out of the way. Now we're going to square everything out here that we have underneath the square root. So we're going to get the square root of cosine squared alpha minus beta minus 2 cosine
alpha minus beta. Yeah, and then we're going to get plus 1 at the end. And then we're going to have, if I multiply out, so that was multiplying out the left-hand side, just distributing there, write them next to each other, FOIL it out. And then if I do the same thing here, well, we can just kind of ignore the minus 0. I'm just squaring sine of alpha minus beta, so this is going to give me just plus sine squared alpha minus beta. So now if I'm looking for things to simplify in the radicand here, let me just make this smaller and move it up out of the way. I'm seeing another Pythagorean identity in here. I am noticing that we have a cosine alpha minus beta plus, or I'm sorry, cosine squared alpha minus beta, the square is important, plus sine squared alpha minus beta. Those are just giving us 1. I have another one here, plus another one, and then I've got, well, let me maybe color this other one in green, since it was already there. And then I've got minus 2 cosine alpha minus beta. So if I want to clean that up, we'll get the square root of 2 minus 2 cosine alpha minus beta. Okay, so that is how this second part simplifies. So the distance from A to B is equal to the square root of 2 minus 2 cosine alpha minus beta. So we can add that to our list of things that we know now. And now we're getting ready, finally, after about 20 minutes here, of getting our conclusion. So we know that this distance from P to Q can be written in the green there. And we know that this distance from A to B can be written in what I circled in the purple there. So if those distances are equal, since PQ, maybe I'll do this back in yellow, since PQ is equal to AB, or the distances, maybe I should say to be super clear here, between those are equal, I can set them equal to each other. So is what we will do here. We are getting that, I'll do it down here again, and if I need more room I can move it up and make it smaller. The square root of 2 minus 2 cosine alpha cosine beta minus 2 sine alpha sine beta. That was the part in the green there. Probably should have done that in green maybe. But that's going to be equal to the part I circled in pink here, the square root of 2 minus 2 cosine of alpha minus beta. Now we're just going to see if we can't simplify and try and get the relationship that we want. So if we square both sides here, I'm going to do maybe kind of a cheat move here with the iPad. But if I square both sides, then we're undoing the square roots. So for the sake of my space here, I'm just going to undo these square roots and just delete them. So we're getting this now. So I've squared both sides to get rid of the square roots at this point. And now I'm noticing I can subtract 2 from both sides. And I can cancel out these 2's. And now if I divide both sides by negative 2, divide by negative 2, we're getting those canceling. And that negative 2 is canceling. In fact, maybe I should do this in a little bit more of a legit way. I don't want to skip steps here and lose us. So let me move this up now that I've subtracted 2 from both sides. Let's get rid of this. Oops. Okay, I've subtracted 2 from both sides. Let me factor out a negative 2 from the left-hand side. So I get negative 2 cosine alpha cosine beta plus sine alpha sine, this should have been a beta, sorry, that should have been a beta the whole time, sine beta is equal to negative 2 cosine alpha minus beta. Now we'll divide both sides by negative 2. Cancel, 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 and we get the result. If I write the right-hand side on the left-hand side now, we get that the cosine of alpha minus beta is equal to the cosine alpha cosine beta plus sine alpha sine beta. So there it is. There is our difference formula that we claimed. I know this was a long, convoluted process to get there, but it is the process that gets us there. So we have a proof now. We know that the cosine of alpha minus beta is equal to the cosine alpha cosine beta plus the sine alpha sine beta. So there's our proof, and we can give a little QED here at the end, or a little filled in box, whatever you want to do to conclude our proof here. So there it is. Here we get the rest of the sum and difference formulas for cosine and sine. So this is the guy that we just proved here. We can use what we know about negative angles and the odd and even properties of sine and cosine to get this formula. And then we can do something similar. We can think about the shift between cosine and sine being pi over 2 to go from here to here. I'm just hand waving some of these other arguments just to get us the rest of these here quickly. And then we can do the same thing that we did to get the other version of cosine, is use the even and odd properties of sine and cosine to get the fourth one. So those are good exercises, and maybe we can talk about those going forward. But for now, we want to get into using these here. So I've got the cosine of 5 pi over 4 minus the minus pi over 6. So we want to use the difference formula here that we just developed, and we're going to get that the cosine, if I call maybe this alpha and this beta, we've got alpha minus beta, so we want to use this formula here. So we're going to get cosine of alpha, which we're calling 5 pi over 4, times the cosine of beta, which we're calling pi over 6, and that's positive because the subtraction happens in between alpha and beta. And then we will add to that the sine of alpha, which is 5 pi over 4, and we will multiply that by the sine of beta, which is pi over 6. Okay, so there we go. We've just rewritten the problem in terms of its difference formula here. And now we just want to go compute what each one of these different values are. So either you've got them memorized, or if you're like me, you like to just go double check quickly on a unit circle here. So I'm just going to label these angles on here. We're looking at 5 pi over 4, and 5 pi over 4 is going to be over here. This is 5 pi over 4, and down here this is a value of negative square root of 2 over 2. Negative square root of 2 over 2. That is that point down there. The cosine's on the left, the sine is on the right. They both happen to be negative square root of 2 over 2. So I can go plug those in just a second here. And I'm also looking at pi over 6, which is this angle here. And this point is at the cosine is square root of 3 over 2. And the sine value is 1/2. So I like to just write these down explicitly, because now I can just go plug things in. The cosine of 5 pi over 4 is negative square root of 2 over 2. The cosine of pi over 6 is square root of 3 over 2. I want to add to that the sine of 5 pi over 4, which is negative square root of 2 over 2. And I want to multiply that by the sine of pi over 6, which is 1/2. And if I simplify this guy here, I'm going to get negative square root of 6 over 4 plus negative square root of 2 over 4. So this gives me negative square root of 6 minus square root of 2 all over 4. So here we go. Here is the difference, the cosine of the difference of those two angles there. And you'll notice as we do a lot of these problems, we'll see a lot of square roots of 6 showing up, and lots of square roots of 2 all being over 4. That'll be a common thing that we'll find, at least when we're kind of looking at these contrived angles that happen to show up in math classes. So there we go. I think we'll get some practice using a few more of them here. So we want to find the exact value of the cosine of 75 degrees. So now we're doing things in terms of degrees instead of radians, but it's all the same here. This isn't exactly written as a sum or difference of angles here. And we also don't know the cosine of 75 degrees. It's not one of those exact values that we know. But I could rewrite 75 degrees as a sum or difference of angles that I do know. So what I'm saying is that we could rewrite cosine of 75 degrees as the cosine of 45 degrees plus 30 degrees. And now we can use facts that we know about cosine of 45 degrees and cosine of 30 degrees and sines of those values to get what we want here. So these say the same thing. 45 plus 30 is going to give us 75. And now if I rewrite this in terms of the sum formula for cosine, we're going to get cosine of 45 degrees times cosine of 30 degrees minus sine of 45 degrees times cosine. Whoops. Cosine of, nope, sorry, another sine. I'm on autopilot, sine of 30 degrees. So for the cosine, you get cosines together and the sines together, and the sine is what is different here. The plus happens in the argument, and that turns into a minus in our formula here. So now I'm just thinking, all right, well, what are these different values here? If I can't remember, I'll just go graph them quickly on a unit circle. I'm looking for cosine of 45 degrees. I'm going to need the sine as well, but 45 degrees is going to be at square root of 2 over 2, square root of 2 over 2 on our unit circle, and 30 degrees, we just found this one before as well, is going to be at square root of 3 over 2, and then 1/2. So we can just use these values and plug them in. I know that the cosine of 45 degrees is square root of 2 over 2. I know that the cosine of 30 degrees is square root of 3 over 2. And I want to subtract the sine of 45 degrees, which is square root of 2 over 2, and the sine of 30 degrees, which is 1/2. And here we will get square root of 6 minus the square root of 2 all over 4. So like I said, we'll start to see a lot of answers that look like this form, and they'll be subtraction and addition symbols in different places here to make sure we're getting the proper values. But there's that one. So the idea is to just rewrite that argument, the 75 degrees, as some angles that we actually know the sines and cosines of. And we'll do the same thing here. I'm looking at the sine of 15 degrees, which I don't know, but I could write 15 degrees as maybe 45 degrees minus 30 degrees. And then we can just use our same picture, I think, from above to get these values. But using our formula for sine, the difference formula for sine, we're going to get sine of 45 degrees, cosine of 30 degrees. So now we're mixing up the sines and cosines and the values here. I know I'll have subtraction because I have subtraction here. And then I'll have sine of the other angle. If I took sine of 45 degrees, now I want sine of 30 degrees. And if I did cosine of 30 degrees, now I want the cosine of 45 degrees. So just making sure I'm switching everything up. That's how I remember the different formulas here. Okay, so sine of 45 degrees is square root of 2 over 2. The cosine of 30 degrees is square root of 3 over 2. We're multiplying those together. We're going to subtract off the sine of 30 degrees, which is 1/2. And the cosine of 45 degrees, which is the square root of 2 over 2. And if I simplify here, we're going to get the square root of 6 minus the square root of 2 all over 4. And if you notice, that's exactly what we got in the previous one. And when I first did this, I thought, well, that can't be right. Something weird has to be going on here. Let me think about the geometry and these angles of this situation and see if this should make sense. And it actually does. So let's just draw a quick unit circle here. Since I was noticing that, oh, we got the same answer, I wanted to make sure that I didn't make a mistake. Okay, so 75 degrees, I'm looking at 75 degrees is, 60 degrees is about here, so that means that 75 degrees is going to be halfway between that and 90. And if I'm looking at that cosine value, yeah, it's going to be like pretty dang close. I'm sorry, the other way. It's going to be, if I want the cosine of 75 degrees, it's going to be this value right here, which is a pretty small value. And then doing the same thing with the sine of 15 degrees. We know that 30 degrees is about there, which means that 15 degrees is going to be halfway down. And if I want the sine of this here, well, yeah, that is a pretty short degree. And yeah, these look to be about the same. So I'm guessing that those values would be the square root of 6 minus the square root of 2 all divided by 4. But yeah, okay, these make sense. They're both just 15 degrees off from a main angle, either 90 degrees or 0, and since we have the sine and the cosine, they're co-functions. Okay, this is all making sense to me here. So didn't need to do that extra bit in green. We got the answer no matter what. I just wanted to make sense of these answers and make sure that they are what they say they are. All right, we're going to do a few more of what we just did, but now we're dealing with radians instead of degrees, and these can be a little bit trickier just because radians have fractions and pi's in them, and it's weirder to think about adding some angles that we know when we can't see them as clearly like we can with degrees. So Here we're asked to find the cosine of 7 pi over 12. So what we want to do is try and split 7 pi over 12 apart in either the sum or difference of some angles that we do know. And since we have a 12 here, I'm hoping to maybe reduce that 12 with a 2 in the numerator to get a pi over 6, or a 3 in the numerator to get a pi over 4, or a 4 in the numerator to get a pi over 3, or a 2, or a 6 to get a pi over 2, but I'm trying to just split things apart so that I get two things that reduce here, two fractions that reduce. And I think the way that I want to do this here is to use addition, and I want to write this as maybe, I did it with a 3 pi first in my notes, it doesn't really matter, but I did 3 pi over 4 plus, what would I add to 3 pi over 4 to get 7 pi over 4? I would need another, I'm sorry, over 12, not over 4, over 12. And then the 4 pi over 12, so I think I was getting ahead of myself there. But 3 pi over 12 plus 4 pi over 12 does give us 7 pi over 12. And if I reduce each one of these fractions, I'm going to get pi over 4 plus, this is pi over 3. And I do know the cosine of pi over 4 and the cosine of pi over 3, so let me use those relationships to get what we want here. So using the cosine formula for addition, I'm going to get cosine of pi over 4 times cosine of pi over 3 minus the sine of pi over 4 times the sine of pi over 3. Just to quickly get these values in here, cosine of pi over 4 is square root of 2 over 2. Cosine of pi over 3 is 1/2. Minus sine of pi over 4 is square root of 2 over 2. Sine of pi over 3 is square root of 3 over 2. And this is going to give us square root of 2 minus square root of 6 all over 4 once we simplify that guy there. So there we go. Just doing the same thing, but with radians here. We'll do the same thing for the second example. I can rewrite this sine of 11 pi over 12. Trying to think of some sum or difference being over 12. We'll start with sums. Can I split 11 apart into some terms that reduce with this 12 in the denominator to get what we expect? You'll see 12s in the denominators a lot for these problems. So, you know, 5 pi and 6 pi totally work. And 6 pi over 12 does reduce to pi over 2, and that's something that we know, but we don't know 5 pi over 12. So I'm just saying we can make some guesses here, but that one doesn't turn out to be what we want here because we don't know what 5 pi over 12 is. So we can just try some other ways to separate this apart. Maybe I try 3 pi over 12 and 8 pi over 12. Those numerators add to 11, so this is definitely adding to 3 pi over 12, or I'm sorry, 11 pi over 12. And if I simplify here, I do get something nice. I will get the sine of 3 pi over 12 is pi over 4, and then 8 pi over 12 is 2 pi over 3. And those are angles that I do know the values of for sine and cosine. So if I rewrite this guy now, we have a addition for sine, so I'm going to do sine of pi over 4 times cosine of the other angle, 2 pi over 3, and then I will add sine of not pi over 4 but the other angle, 2 pi over 3, and then cosine of not the one I already did, 2 pi over 3, but the other angle, which is pi over 4. So I know that for cosine, it's cosine, cosine, sine, sine, and the angles should be in the right spots. I know that for sine, it's sine, cosine, and that we need to just mix up the angles there. Okay, so sine of pi over 4 is square root of 2. Let me switch back to a pen. Square root of 2 over 2. The cosine of 2 pi over 3, maybe we will go draw a picture here just to make sure I don't mess anything up, since we're using a new angle. Oh, that's not the shape that I wanted. Since we're using a new, go away, there we go. Since we're using a new angle here that we haven't used yet. So we're looking at 2 pi over 3, which is this angle here. And this has a cosine value of -1/2 and a sine value of square root of 3 over 2. So cosine I just said here was negative 1/2. And then plus the sine of 2 pi over 3 is going to be square root of 3 over 2 times the cosine of pi over 4, which is square root of 2 over 2. So once I simplify here, we're going to get negative square root of 2 plus the square root of 6 all over 4. That's a fine way to write that. We could also write this as square root of 6 minus square root of 2 all over 4. So either one of these are fine. But there we go. We are using the sum and difference formulas here to be able to get exact values of angles we wouldn't be able to otherwise. All right, so just a different example here. We are going to suppose that alpha and beta are angles given as follows. So we're told that the sine of alpha is equal to negative 7 over 25, and it is an angle in quadrant 3. And we're told that the cosine of beta is negative 3/5, and it is an angle in quadrant 2. We want to compute the exact value of sine of alpha plus beta. Okay, so I'm just going to start drawing some pictures here. I know that sine of alpha is negative 7 over 25. So let's take a look at this situation here. We are told that alpha is in quadrant 3, so I'm just going to just rough in just whatever, some angle here, and we will call this alpha. I'll drop in my reference triangle so I can use this to figure out what's going on. We've got negative 7 over 25, which means that this is going to be negative, this distance here is negative 7, and this hypotenuse is 25. And if I want to figure out what this x value is here so that I can get the cosine of alpha, well, let's do that. We would get x squared plus negative 7 squared is equal to 25 squared. So we would get that x is equal to plus or minus the square root of 25 squared, which is 625, minus negative 7 squared, which is 49. We're getting x is equal to plus or minus 20, not the square root of 24, but just 24. And we want the negative value since cosine is going to be negative in quadrant 3 here. So I can write in now this other side here we will call negative 24. And if I want the cosine of alpha now, the cosine of alpha, that's going to be negative 24 over 25. So I've got sine of alpha and cosine alpha just by what we were given here about alpha and its sine. Now we'll do the same thing for beta. So let's get rid of this. Let me change colors perhaps. I am told that the cosine of this angle beta is negative 3 over 5. I think that since we're going to need to do sine of alpha plus beta, we're going to need the sine of beta here. So let's think about this situation. We're told that beta is in quadrant 2, so just roughing in some generic beta here. And we know that its cosine is negative 3 over 5. So if we drop in a reference triangle here, we're going to have negative 3, and the hypotenuse is 5. This looks like a 3, 4, 5 triangle to me, so without getting into too much of the details here, with the Pythagorean theorem, I would get that the sine, at least this y value here, is 4, which tells me that the sine of beta is going to be 4 over 5. Okay, so just by giving information about alpha and its sine and beta and its cosine, we're able to get all of the different sines and cosines here. So let me get rid of my unit circles here that I did to figure this out. And what we're asked to do is find the sine, maybe I'll do this in a different color, the sine of alpha plus beta. So this is going to be sine alpha cosine beta plus sine beta cosine alpha. And I know what all these values are. I know that the sine of alpha is negative 7 over 25. I know that the cosine of beta is negative 3 over 5. I can write that a little better. Negative 3 over 5. And then I want to add to that the sine of beta, which is 4/5. And then multiply that by the cosine of alpha. Cosine of alpha is negative 24/25. So if I start to multiply things out here, I would get 21 over 125 plus negative 96 over 125, which gives me negative 75 over 125, which is negative 3/5. So there is our sine of alpha plus beta is negative 3/5, which happened to be the same as the cosine of beta. Just mostly a coincidence here, just happened to be the way that things worked out. I'm sure if we looked at some different relationships, we could prove that that is exactly what we want, but it is what we get here. So there we go. You will see examples like this going forward of just using your knowledge here to be able to find what you want, and then use the sum and difference formulas as needed. Okay, so what we haven't seen yet, we've been doing lots of sums and differences of sines and cosines, but we haven't seen a tangent yet. So let's take a look at tangent. We're going to prove the sum formula here for tangent, and we're just going to use things that we know already from sine and cosine. So I'm going to need a little bit of space here, so we're going to maybe use a few pages to do this, but it's mostly just algebra. But what we're going to start with here is, let me switch colors, the tangent of alpha plus beta, and we're going to do some work, and then we'll show that we will get the other side here. If you notice that the tangent of alpha plus beta does have tangent alpha plus tangent beta in it, it's just then divided by something. So if you're trying to think about how to remember these, tangent of alpha minus beta does have a tangent alpha minus tangent beta, but then we're divided by something, and those somethings look similar in both of these cases here. So okay, so what I'm going to do is rewrite this in terms of sines and cosines. This says the same as sine alpha plus beta over cosine alpha plus beta. Now I can just use the sine and cosine sum formulas to rewrite this as sine alpha cosine beta plus cosine alpha sine beta. You'll notice that sometimes I write the ones here in a different order. I'm just trying to make sure I'm getting everything in the right spot, but the order doesn't matter since multiplication is commutative, so just wanted to point that out here. And then if I rewrite the denominator, I'm going to get cosine alpha cosine beta minus sine alpha sine beta. Okay, now we're going to do a weird step, but is what we need to do to get what we want here. I'm going to multiply the numerator and the denominator by 1 over cosine alpha cosine beta. Oops. 1 over cosine alpha cosine beta. Okay, so now what I have is sine alpha cosine beta, and what I'm doing here is I'm distributing my 1 over cosine alpha cosine beta to each term here. So I've got sine alpha cosine beta over cosine alpha cosine beta, and you might notice that some things cancel out there. That's why we're multiplying by this funky form of 1. It's going to do exactly what we want here. And then to this I want to add this other distribution, cosine alpha sine beta all over cosine alpha cosine beta, and you'll notice that some things cancel out there as well. And that's the numerator of our fraction now, and then in the denominator I'm going to distribute as well, and we're going to get cosine alpha cosine beta all over cosine alpha cosine beta. You'll notice that some things cancel there. In fact, everything cancels there. And then from this, we want to subtract sine alpha sine beta all over cosine alpha cosine beta. Nothing cancels there, but we will get some tangents there. So now we're just going to try and simplify a bunch of stuff. So like I said, I noticed that the cosine beta and the cosine beta are going to cancel. This cosine alpha and this cosine alpha are going to cancel. Everything cancels here to just give us 1. And then over here, if I kind of split this in half, this gives us tangent alpha, and this gives us tangent beta. And they're still being multiplied in the middle there. So what we are getting now, well, here we have tangent alpha, plus here we have tangent beta, all over, here's our 1, minus tangent alpha tangent beta. And there we go. This is what we were looking for. The whole time, if I go back to the top here, that we'd get tangent alpha tangent beta over 1 minus tangent alpha tangent beta. And that's what we get here. Tangent alpha plus tangent beta over 1 minus tangent alpha tangent beta. So there we go. We could use the even and odd properties of cosine, and or just, I guess, the odd properties of tangent to get the other version here. But I will leave that to you to explore for sake of time here. So let's look at an example. Here, we want to find the exact value of the tangent of pi over 6 plus pi over 4. So I will just tell you up front, depending on how you tackle this algebraically and when you rationalize denominators, or etc., your answers might look different from your friend or from what the computer is telling you in the solutions. So just keep that in mind. You might need to just plug things into a calculator and make sure that your solution and your friends or the books agree in case they look a little bit different. I noticed that as I was working through some of these. So I'm just going to use the formula here. And if I have tangent of pi over 6 plus pi over 4, I'm going to get tangent of pi over 6 plus tangent of pi over 4. I know that we do kind of have this relationship here where tangent does just split them apart as expected, but then we need to divide by 1. I remember that I need the opposite sign of what I started off with, minus the tangent of both of them. Tangent pi over 6, tangent pi over 4. Now I just need to know what all these values are, so I'll just draw a unit circle off to the side and remind myself of all of these tangent values. Tangent of pi over 4, that's a straightforward one. That's just going to be 1. So just to get these in here, I know that tangent of pi over 4 is just going to be 1. Tangent of pi over 4 is just going to be 1. The tangent of pi over 6 is more interesting. Pi over 6 is at square root of 3 over 2, 1/2. So if I want the tangent of pi over 6, this is the same as the, if you have this memorized, then you've got it memorized, you can just plug things in. Since I don't have these memorized, I know that this is the same as the sine of pi over 6 over the cosine of pi over 6. Sine of pi over 6 is 1/2. Cosine is square root of 3 over 2. So we get 1 over square root of 3, which if I rationalize the denominator is square root of 3 over 3. So depending on if you choose this for your value to plug in and then rationalize later, or start this with this as your value to plug in for tangent of pi over 6 and then simplify later, your answers might look a little bit different. So I'm using the rationalized form here. So we'd be putting in now square root of 3 over 3 plus 1 all over 1 minus square root of 3 over 3 times 1. So let me make some space here now that I've got these values. Maybe I'll just make it smaller. Oh, I didn't get all of it. Still didn't get all of it, but that's okay. We'll just put this wherever, over here, I guess, in case we want to reference it. But now what do we have? We've got square root of 3. If I rewrite 1 as 3 over 3, then I'll have square root of 3 plus 3 all over 3. So getting that common denominator there, then adding the numerators. And then same thing here, I can rewrite this one as 3 over 3. And then I'll have 3 minus the square root of 3 all over 3. Multiply by the reciprocal of the denominator. Now I've just got complex fractions. I've got the square root of 3 plus 3 over 3 times 3 over 3 minus the square root of 3. A lot of this is a mouthful to say. 3's cancel, and we get the square root of 3 plus 3 over 3 minus the square root of 3. So there's my answer here. Like I said, I noticed, then I checked my solution to see what the book said, and theirs looked different. Theirs looked like where is it? Square root of 3 plus 1 over square root of 3 minus 1. And I was like, oh no, I must have made a mistake somewhere. But if you plug them into the calculator, these are actually equivalent expressions. And you can show that they are the same because if you use 1 over the square root of 3 as your values for tangent of pi over 6 and simplify, you would get this version instead. So they say the same thing. I was surprised to see that, but it is true and kind of an interesting fact there. So, all right, from there it is time to practice. So I will leave it there. If you have questions on the homework, please let me know. I'm always happy to help. I'll see you in our next video.